I'm going to talk to you about check understanding from chapter 10 is a classic kind of quadratic word problem. This is throwing things up in the air and let it fall down type of problem. If you've ever noticed, hopefully you've noticed that if you throw something up in the air, it follows a parabolic path. So we're going to take a look at an aspect of that. So this is called the height equation, or the free fall equation. So H represents height, T is representing time, and on your Desmos, of course, you can replace T with X because it'll work graph-wise. But so T equals time, and then we've got these coefficients. We've got this funny coefficient, 16. So you know the Earth's gravitation is negative 9.8, probably, or negative 9.81 per second squared. It might only express negative 32 feet per second. If we want to step out of the sensible metric system and use the English system of feet and inches. You might be wondering why that negative 32. That's because the equation to figure out how far something has gone in a particular amount of time, if you have the same acceleration, is 1/2 times acceleration times time squared. So this here is a simplified version of 1/2 times negative 32 times the time squared. This is the distance you get for a specific acceleration times time for a particular amount of time. So we don't know our time, but we substitute time squared here. This tells me that our acceleration is negative 32 feet per second squared, so we're on the Earth. And it also tells me everything else is going to be in feet and seconds. V stands for velocity, whatever our initial starting velocity is. And 3 is our starting height. And it says this all here. So initial upward velocity is V. Now, if it were downward velocity, that would be a negative number. Our starting height is C. So we've been told in this example that our starting upward velocity, our initial upward velocity, is 47 feet per second. So replace that with 47, that's velocity. And the starting height for the kick was 3 feet in the air. So we just have these numbers, and this gives us a standard form quadratic equation. And our questions, no one catches the football, how long will it be in the air? Well, how long is the t part? So we're trying to figure out what t is. It could just as well have been x, but we need t to represent time. So if height is what this is, when it reaches the ground is how long, the length time it's going to be in the air, the length of the time for it to go up in the air and then come back down to the ground where it has a height of 0. So hopefully I've demystified this a little bit for you. So replacing the height with 0 because we want to know how long it'll be before it hits the ground. We've replaced the velocity with 47 and 3 for our constant, which is how high we started to begin with. We can take all of that information and plug it into our quadratic formula. So this is half our gravitational acceleration. So, and that's A. So A becomes 16. And B was 47. Is our starting velocity. And C was 3 feet in the air to start off with. We get two answers here. An answer that's negative times. That's negative time. That means it's in the past. And this part is actually irrelevant. We would disregard it as extraneous because it's in the past. There wasn't really a past for this process before we kicked the ball. But the part that is relevant is the future. We want to know how long until it hits the ground. It's going to take 3 seconds. And so we can go ahead and plug all the stuff in. Okay, so I had 47 for B. That's our B is our velocity. A is negative 16. B is going to be 3. I'm sorry, C, is 3. So negative 16 is our A, C. And then down here, we're going to plug in negative 16 again. And we've got all that plugged in. We could work it all out and simplify it. I'm going to copy that. I'm going to give us the negative or minus version because our square root has got a plus or minus part of it. And we get the same answer. So all those numbers are plugged right in. And we could go through the process of simplifying it. I'm going to leave that to you because I think it's going to be some good practice for you to do all this. This is one of the reasons we kept emphasizing the order of operations over the last few years, because you're going to have to use operations to simplify this. You're going to have to first deal with everything in this grouping symbol of the square root. You just have to square that. You have to do the multiplication. Then you can put those two parts together. Then square root. You have to deal with this by itself, and then you'll have all your pieces. But go step by step. The order of operations, GEMDAS, grouping, exponents and roots, multiplication and division, addition and subtraction. Take a look at the actual problem they give us for exercise 3, in which, and they say the football will be up in the air for 50 seconds in the example. The football kicked the ball initial outward velocity of 38.4 feet per second, initial height of 5. Okay, so we have our initial velocity, starting height. But they haven't said anything about our acceleration. You can assume, if they don't say we're not on the Earth, you can assume you're on the Earth. The Earth's gravitational acceleration is going to be negative 32, and the first part of that equation ends up being 1 acceleration times squared. So negative 32 times a half is 16. So we're going to use that part again. So let's plug in our A is going to be negative 16. Okay, got that. This is, I believe, 38.4 velocity was, and our initial is 3.5 feet. Okay. Now, another reason I knew negative 16 here, which is half of negative 32 feet per second squared. I knew it was negative 32 feet per second squared instead of negative 9.8 meters per second, because everything is in terms of feet in this story. So we can then take all of this stuff and plug and play. So we know that our A continues to be negative 16. I'm just going to replace A wherever it shows up, negative 16. We know that our B is 38.4. And this also is 38.4. And then that's squared. And then we find any place our C is and replace it with 3.5. And so we get all that stuff. This is pretty ugly, and it gives us a pretty ugly answer, which we would end up rounding, but that's negative, so we're going to ignore it because that's in the past. And in the past, the football was probably being held by someone instead of sailing through the air. So we've got that version, and we need the or minus version. This is the negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so I now have a positive in seconds, and this is our answer. It's in the future. If I round it to the nearest hundredth, it's 2.49 seconds in the future. So our answer is our answer that we care about is 2.49. That is how long the ball will be. Okay. The part A used into that vertical formula. And then we solved it. One catches the ball. How long will it round to the nearest tenth of a second? Incidentally, there's some other information we can get from this. We can find out how high the ball went. We can figure out how long it took the ball to get to the highest point. And here's how we can do that. We can do it two ways. The highest point is going to be the y value at the vertex. So the vertex, the x value for the vertex is negative b over 2a. Okay, so the x value for the vertex is negative b over 2a. So if we said negative 38.4 over negative 16 times 2, we would have it. So I'm going to set that up, negative b over 2a. And it's going to be 1.2 seconds. And then you might be wondering, how do I figure out how high it went? Well, let's just create our equation. Negative 16 t squared plus 38.4 t plus 3.5. And then if I replace, so I'm going to take that. I've made a little slider for t. So I'm going to replace t wherever it is here with 1.2. Everywhere there, t is 1.2. And so it's going to be many feet here, 26.54 feet here. Believe me on that, that's okay. We'll prove it. I'm going to replace t directly instead of using a sneaky slider. Okay. So t is now going to be 1.2 and 1.2. And if I felt like it, I could go ahead and square 1.2, which would be 1.44. And I could multiply negative 16 times 1.44, add that to 38.4 times 1.2, and add that to 3.5, and I'd get this. But that is our answer for how high the ball gets after 1.2 seconds when it's at its vertex. And then I'm going to demonstrate that just a little further. We'll say y equals negative 16x. I'm going to use x instead of t here, squared plus 38.4x plus 3.5. And here we have our little parabola. Bring that down a little bit so it's a little easy to see. Okay, so see what shows up on the right there is my y-intercept. My y-intercept is my height at my y-intercept is how high the ball was when it started. This is the extraneous answer back in the past, which we don't care about, so I'm going to ignore it. This is how long it took before it hit the ground, which was the 2.49 when I rounded. And this is how high the ball went in the air, 26.54 feet after 1.2 seconds. Okay, so that is information we can get from this. We could figure out how long it took the ball to get to 20 feet. So if we said y equals 20, we have a horizontal line at all I values at 20 feet. Okay, it gets there in 0.56 seconds, and then it comes back down there in 1.84 seconds. I rounded 1.839 there. And we could change that up and down, and so if I lowered that to, say, 9 feet, we could find out that the ball made it 9 feet in 0.15-ish seconds, and went up, and then came back to 9 feet in about 2.25 seconds. So hopefully this has given you a little clarity around this particular problem. To recap, what we're dealing with is called the vertical motion formula. And we'll start off with three different expressions for height. So height is given to us by three different things. It's given to us by starting height, which has to do with our height, and then if our height is changing because we get initial velocity, a lot of time will give us a height as well, if that's a vertical velocity. All velocity versus time equals displacement. We're just talking about a vertical one, which we call height. So this is velocity times time. This is 1/2 times acceleration times time squared. Acceleration was negative 32 meters per second squared. This is the acceleration expression in terms of time for how high something is gone. Expression for how high something is gone, and just how high it when it began. So that together, we're just putting three different ways of expressing the height, the overall height, because you've got different pieces of this, where you start, how fast you're going to begin with, and how much gravity is changing how fast you're going, are all the pieces of this equation. And we can do a lot of applications with, and we will have a lot of fun with those problems. I can't wait. Here we go.